Right now, somewhere in the constellation Aquarius, 40 light-years from Earth, 7 worlds are rising in the same sky. Not stars, not distant galaxies, planets, each one large enough to hold oceans, close enough to see weather systems swirling across their faces, near enough that if you stood on the surface of one, you could watch the others drift across the horizon like luminous moons casting coloured shadows on alien seas. This is not science fiction. This is TRAPPIST-1, a planetary system so tightly bound that all 7 worlds could fit inside the orbit of Mercury. They move together in mathematical precision, their orbits locked in gravitational harmony. When one completes 3 revolutions, another completes exactly 2. When one circles 5 times, its neighbour circles 4. They are synchronized, choreographed, as if the universe itself were conducting. We thought we understood solar systems, planets scattered across vast distances, each one isolated in its own orbit, separated by millions of miles of darkness. Mercury, Venus, Earth, Mars, each inhabiting its own private sphere, never close enough to see each other as more than wandering points of light. We believed that was normal. That distance was a requirement for stability. We were wrong. The universe has been building something far more intimate. Systems where worlds orbit so close they could almost touch, where planets reflect each other's light across alien atmospheres, where gravity doesn't isolate but connects, weaving multiple worlds into a single breathing structure. These are the worlds inside worlds, planetary systems so densely packed, so perfectly balanced, that they challenge everything we thought we knew about how solar systems form, evolve, and endure. Tonight we fall into one of these systems. We drift through skies that are never empty, where horizons are crowded with neighbouring worlds, and where the night is painted not with distant stars but with the faces of sibling planets. We will stand on surfaces where 3 moons rise at once. We will watch as gravity composes music across space. We will witness what happens when worlds share not just a star, but a destiny. Because in these systems, proximity is not chaos, it is architecture. The universe doesn't just scatter planets randomly across the void, it arranges them, it tunes them, it creates structures so delicate and so precise that they border on impossible, yet they exist. Dozens of them discovered in the last decade alone, each one a testament to nature's ability to build complexity out of emptiness. And perhaps in discovering these densely packed systems, we are discovering something about ourselves. We have always imagined ourselves as lonely, a single pale blue dot suspended in cosmic isolation. But what if loneliness is the exception, not the rule? What if the universe prefers to build neighbourhoods rather than hermitages? What if life, when it emerges, looks up at a sky filled not with unreachable stars but with reachable worlds? The planets are waiting, their orbits already in motion, their rhythms already synchronized. All we have to do is listen. The star at the centre of TRAPPIST-1 is an imposter. From a distance it looks like a star. It glows, it burns, it fuses hydrogen in its core. But place it next to our sun and the illusion breaks. Our sun would dwarf it, a blazing giant next to a dim ember. TRAPPIST-1 is barely larger than Jupiter, small enough that if it had formed with just slightly less mass, it would have failed to ignite at all, remaining a brown dwarf, a stellar corpse that never lived. Yet around this tiny sun orbit 7 worlds, packed so tightly that the entire system would fit comfortably inside the orbit of Mercury. If you could shrink our solar system down and overlay it on TRAPPIST-1, Earth would be somewhere past the outermost planet, drifting in empty space beyond the edge of their architecture. This nearness defies our intuition. We learn the solar system through a particular template. Vast distances, ordered spacing, each planet given room to breathe. The asteroid belt separating the rocky inner planets from the gas giants. The Kuiper belt marking the boundary of the known. Everything spread across billions of miles, arranged by some invisible hand that preferred separation. TRAPPIST-1 rejects that template entirely. Here, proximity is not dangerous, it is the foundation. The innermost planet, TRAPPIST-1b, completes an orbit in just 36 hours. It circles its star at a distance of 1.7 million kilometers, 10 times closer than Mercury orbits our Sun. At that distance it should be tidally locked, one face perpetually scorched by starlight, the other frozen in eternal darkness. And it is. But the star it faces is so dim, so cool, that even the day side remains temperate, heated not to thousands of degrees but to a few hundred. Move outward. TRAPPIST-1c orbits at 2.4 million kilometers, completing its year in 2.5 Earth days. TRAPPIST-1d at 3.3 million kilometers, 4 days. TRAPPIST-1e at 4.2 million kilometers, 6 days. Each one slightly farther, slightly slower, but still impossibly close by the standards of our own system. If you stood on TRAPPIST-1e and looked toward the inner system, the other planets would not be distant points of light. They should be disks, visible to the naked eye, large enough to show features. TRAPPIST-1d would appear roughly the size of our moon seen from Earth. TRAPPIST-1c, smaller but still distinct. On clear nights, you could watch weather systems evolve across their faces in real time, clouds forming and dissipating over the course of hours. The question that haunts astronomers is simple. How does this not collapse into chaos? Gravity is unforgiving. It does not negotiate. When objects orbit too close to each other, their gravitational fields interfere, tugging at each other's paths, amplifying tiny perturbations into larger and larger deviations, until orbits become unstable. Planets swing too close, collide, or get ejected entirely from the system. This is not theoretical. We have watched it happen in computer simulations thousands of times. Place 7 planets this close together with random orbits, and within a few million years most configurations tear themselves apart. Yet TRAPPIST-1 has survived for billions of years, not by avoiding gravitational interference but by embracing it. The key is resonance. Each planet's orbit is not independent. Each one is coupled to its neighbours through precise gravitational timing. When TRAPPIST-1b completes 8 orbits, TRAPPIST-1c completes exactly 5. This means that every time B completes 8 full circles, it returns to the same position relative to C. Their gravitational tugs happen at the same points in their orbits, creating a pattern that reinforces rather than disrupts. Think of it as conversation with perfect timing. If 2 people speak over each other randomly, the result is noise, but if they take turns, if they respond to each other's rhythm, the conversation flows. The planets of TRAPPIST-1 have learned to take turns. Their gravitational influences, instead of interfering chaotically, create a stable pattern that has endured since the system's formation. This stability comes at a cost. The orbits cannot drift. The planets cannot migrate inward or outward without breaking the resonance chain. They are locked in place, bound not just to their star but to each other. Each world listens to the gravitational heartbeat of the next, adjusting its motion to match, maintaining the rhythm that keeps them all from falling. The mechanism that created this architecture is migration, but migration of a very specific kind. In the early solar system, when TRAPPIST-1 was still surrounded by a disk of gas and dust, the planets did not form where we see them now. They formed farther out, beyond what we now call the snow line, the distance from the star where temperatures drop low enough for water to freeze. Beyond this line, ice becomes abundant, providing the raw material for planets to grow quickly, accumulating mass until they become large enough to hold atmospheres. As these young planets grew, they began interacting with the protoplanetary disk. The disk's gas exerted drag on the planets, slowing them down, causing them to spiral inward toward the star. But they did not spiral alone. Multiple planets migrated simultaneously, and as they moved inward they encountered each other. When two migrating planets approach, their gravitational interaction can go one of two ways. They can scatter, flinging each other into chaotic orbits, one flung outward, one sent crashing toward the star. Or they can lock into resonance, their orbits synchronizing, their migration slowing as they begin to move together. In TRAPPIST-1, resonance won, not just between two planets, but across the entire forming system. As each planet spiraled inward, it encountered the one ahead of it and locked into resonance. Then the next planet arrived and locked with both. Then the next. The process cascaded, building a chain that eventually included all 7 worlds, each one linked to its neighbours through gravitational harmony. By the time the protoplanetary disk dissipated, blown away by stellar winds and radiation, the planets had already settled into their final configuration. The migration stopped, but the resonances remained, freezing the system into the architecture we observe today. This process explains why so many compact planetary systems show resonance chains. It is not that resonance is rare, it is that resonance is the natural outcome when planets form close together and migrate through a shared disk. The universe does not need to fine-tune these systems into existence. The physics does it automatically, but the architecture is not invincible. Computer simulations show that even small perturbations can break resonance chains. A passing star swinging too close could gravitationally nudge one planet out of alignment. The loss of a single link would cascade through the system, destabilizing the others, potentially ejecting planets or sending them crashing into the star. The TRAPPIST-1 system has survived for roughly 8 billion years, but it exists in a relatively quiet region of space, far from the dense star clusters where close encounters are common. There is also the question of what happens as the system ages. Red dwarfs like TRAPPIST-1 burn so slowly that they will remain stable for trillions of years, far longer than the current age of the universe. But over those immense timescales, even the smallest gravitational effects accumulate. Tidal forces gradually circularize orbits. Resonances shift slightly. Eventually, perhaps in hundreds of billions of years, the system might drift out of its current configuration, not catastrophically but slowly, like a piece of music gradually changing key. For now, though, the architecture holds. Each world maintains its position, its orbit locked to its neighbours, its rhythm synchronized. The system is a house of cards built from gravity, delicate in its balance, but stable as long as nothing disturbs it. And the stability allows something remarkable: predictability. From Earth, astronomers can predict when each planet will transit across TRAPPIST-1's face with precision measured in seconds. Years in advance, they know exactly when TRAPPIST-1 will cross the star, when its silhouette will block a tiny fraction of the star's light, when the dimming will begin and end. This predictability is not just useful for observation. It tells us something profound about the system's past and future. If the orbits were unstable, if the planets were slowly drifting, the transits would arrive earlier or later than predicted, gradually falling out of sync with the models, but they don't. The timing remains exact. This means the system has not changed significantly in the time we've been watching it, and likely has not changed significantly in millions of years. The architecture is not just stable for now, it is stable across deep time. Each world in this system does not orbit in isolation. Each one feels the presence of the others, constantly through the subtle flexing of space-time. If you were standing on TRAPPIST-1e, you would not notice this directly. There would be no sudden jerks, no earthquakes timed to orbital positions, but sensitive instruments would detect it. Tiny variations in the planet's rotation, slight wobbles in its axis, the faint tidal bulge caused by the combined gravitational pull of your neighbouring worlds. These tidal forces are weak, far weaker than the tides Earth's moon raises in our oceans. But they are constant. Over billions of years they have shaped these worlds, circularizing their orbits, synchronizing their rotations, smoothing out the eccentricities that might have destabilized the system. In effect, the planets have taught each other how to behave. Through billions of years of gravitational conversation, they've refined their orbits, adjusted their rhythms, settled into a configuration where each one's motion supports the others. It is not intelligent design. It is natural selection applied to planetary systems. The configurations that survive are the ones where resonance creates stability. Everything else tears itself apart. Perhaps stability is not distance but rhythm. Perhaps the lesson of TRAPPIST-1 is that worlds need not be isolated to be safe. They need only to listen to each other, to move in harmony, to let gravity connect them rather than scatter them. Because in this system, nearness is not chaos, it is architecture. And the architecture has stood for 8 billion years. The horizon never sleeps. You stand on the terminator line of TRAPPIST-1e, the boundary between eternal day and perpetual night, where the sun hangs motionless just above the edge of the world. The sky glows deep crimson, thick with the scattered light of a red dwarf star. Behind you, darkness. Ahead, a dim twilight that never brightens into noon, never fades into full night. But the sky is not empty. 3 planets hang overhead, each one visible as a disk, not a point. The nearest appears half again as large as our moon, its surface mottled with dark continents and bright polar caps. You can see clouds moving across its face, vast spiral patterns that take hours to rotate into view. It does not rise or set, it simply exists there, perpetually, drifting slowly through the same quadrant of sky as your world spins beneath it. Farther out, a second planet glows pale blue, smaller, half illuminated by the star you both orbit. Its crescent changes gradually over days, waxing and waning as it moves through its orbital phases. Sometimes it passes in front of the sun, and when it does, the temperature drops 10 degrees. The light turns copper, shadows sharpen. The world holds its breath. Beyond that, barely visible against the background stars, a third planet moves in the outer reaches of your system. It appears the size of Venus seen from Earth, bright enough to cast faint shadows at night, large enough that careful observers can distinguish its shape. It does not twinkle, it glows steadily, a beacon marking the edge of your planetary neighbourhood. This is what it means to live in a compact system. Your neighbours are not distant abstractions, they are present, tangible, part of the daily experience of existing. When you look up, you do not see emptiness punctuated by stars. You see other worlds, each one moving through its own day and night, each one carrying its own weather, its own geology, its own story written in reflected starlight. On Earth, we see Venus and Mars as wandering stars, bright but featureless, their surfaces hidden by distance and atmospheric haze. The ancient observers who tracked their motions across the sky could only imagine what those worlds might hold. Here, imagination is unnecessary. The planets reveal themselves directly. From the surface of TRAPPIST-1e, you watch TRAPPIST-1d complete its rotation every 13 hours. You see its continents wheel past, darker patches that might be oceans, brighter regions that could be ice or desert. You observe weather systems develop and decay, massive cyclones that dwarf Earth's hurricanes, spinning slowly across alien latitudes. When storms form on the neighbouring planet, you see lightning flickering along their edges, brief flashes too distant to hear, but bright enough to register against the planet's dim reflected light. You watch seasons change, if seasons exist there, ice caps advancing and retreating, cloud patterns shifting with orbital mechanics you can predict months in advance. And occasionally, during what astronomers call a mutual event, two planets align perfectly. One passes in front of the other. For a few hours, you watch as the nearer world's silhouette transits across the face of the farther one, a planet eclipsing a planet, a sight that would never occur in our solar system's scattered architecture. The colours alone would be impossible on Earth. Red dwarf light is fundamentally different from the yellow-white light of our Sun. It peaks in the infrared, barely touching the visible spectrum. To human eyes, everything would appear muted, tinted red and orange, as if the entire world existed in eternal sunset. But the planets reflecting that light would each add their own tint. A world with a thick carbon dioxide atmosphere might glow faintly orange, its air scattering the red light into deeper hues. A planet with water clouds would shimmer silver white, ice crystals catching and reflecting whatever light reaches them. A world with volcanic activity might show dark smudges of ash, grey stains spreading across its visible hemisphere, clearing slowly as winds redistribute the debris. At night, on the dark side of your tidally locked world, the sky transforms entirely. The sun no longer dominates. Your neighbouring planets become the primary sources of light. The nearest one, catching the full illumination of the star you cannot see from your position, glows bright enough to read by. It casts shadows. Animals navigate by it. Plants might even orient toward it, tracking its slow drift across the sky as your world rotates beneath. When multiple planets align on the night side, their combined light creates a phenomenon unknown on Earth: planetary twilight. The sky never achieves true darkness. Instead, it glows with the accumulated reflection of multiple worlds, each one contributing a fraction of the starlight it receives, together creating enough illumination that the landscape remains visible, eerie and colourless, but navigable. During rare configurations, when 3 or 4 planets cluster in the same region of sky, the night side experiences what could only be called a planetary conjunction. The combined light rivals the brightness of Earth's full moon. Shadows become multiple, each planet casting its own distinct silhouette, overlapping and shifting as the worlds continue their slow orbital dance. And then there are the transits. When a planet passes between you and the Sun, it does not vanish. Instead, you see it silhouetted against the star's disk, a black circle slowly crossing the crimson background. The transit takes hours, sometimes the better part of a day, depending on the planet's size and orbital speed. As it crosses, the light dims gradually. The temperature follows. Weather patterns shift in response, winds accelerating or calming as the surface adjusts to the changing heat. If you were standing on the day side during such a transit, you would experience something like an extended eclipse, but gentler, less dramatic. The sun would dim but not disappear. The world would cool but not freeze. It would feel less like night and more like the shadow of a passing cloud. Except the cloud is a planet, and the shadow lasts for hours. Some transits are predictable, recurring on schedules measured in days or weeks, tied to the orbital resonances that lock the system together. Others are rare, requiring specific alignments that might occur once a year, once a decade. Civilizations on such worlds, if they exist, would track these events with precision, building calendars around them, measuring time not just by the rotation of their own world, but by the dance of their neighbours. In our solar system, we track time by the sun and moon, by solstices and equinoxes, by the phases of Earth's single satellite. In TRAPPIST-1, time would be layered, complex, marked by multiple overlapping cycles. The day would be defined by your world's rotation, the month by the orbital period of your nearest neighbour, the year by your own circuit around the star, and threading through all of it, the transits, the conjunctions, the mutual events, creating a temporal tapestry far richer than anything we experience. The psychological impact of such a sky is difficult to imagine. On Earth, we look up and see vastness, distant stars, unreachable galaxies, a universe that exists beyond any hope of physical contact. We are cosmically isolated, a single world in an ocean of emptiness. That isolation has shaped our philosophy, our religions, our sense of place. We're alone, and the universe is indifferent. But in a system like TRAPPIST-1, isolation would be impossible to feel. Every time you looked up, you would see evidence of other places, other surfaces, other horizons. You would grow up watching worlds drift across your sky, observing their seasons, tracking their changes. The universe would not feel empty. It would feel crowded. Would such a civilization develop differently? Would they assume, as we did not, that life was common, that their neighbours might also be inhabited? Would they look at the nearby planets and wonder not if, but when they would make contact? Or would familiarity breed indifference? Would the planets become mere fixtures of the sky, unremarkable after generations of observation, their presence noted but not pondered, like clouds or mountains? Perhaps both. Perhaps the planets would be simultaneously ordinary and profound, part of the daily backdrop of existence. But occasionally, on clear nights when the alignments were perfect and multiple worlds hung visible at once, someone would stop and look up and feel what we feel when we contemplate the cosmos. Awe at the improbability of it all, wonder at the beauty of natural law, humility before the scale of creation. From the surface of any of these worlds, the universe would not need to be imagined. It would be visible, present, immediate. Your neighbours would not be hypothetical. They would be there, in the sky, waiting. All you would have to do is look up, and if you listened carefully on nights when the air was still and the planets aligned just so, you might convince yourself you could hear them. A faint hum carried across the void, the gravitational music of worlds moving in harmony, a song that has played for billions of years and will play for billions more. The sky never sleeps, and neither do the worlds within it. The question is not whether life could emerge in such a system. The question is whether it could remain confined to a single world. TRAPPIST-1, the fourth planet from the star, sits squarely in the habitable zone. Its surface temperature hovers near freezing, cold by our standards, but warm enough for liquid water to persist. The star's dim red light provides energy, less than Earth receives, but sufficient for chemistry to operate, for reactions to proceed, for complexity to build. If life began there, it would face challenges unknown on Earth. Red dwarf stars are violent in their youth, prone to massive flares that strip atmospheres from nearby planets, sterilizing surfaces with radiation. But TRAPPIST-1 is old, 8 billion years, twice Earth's age. Its flares have calmed. Its output has stabilized. Any world that survived the turbulent early years now exists in relative peace. The conditions are strange but not hostile. The perpetual twilight of a tidally locked world would create temperature gradients, warm regions facing the star, cold zones on the night side, and between them a habitable band where conditions moderate. Water would flow from the day side where it evaporates to the night side where it freezes, and back again through atmospheric circulation. This constant movement would create weather, distribute heat, prevent the atmosphere from collapsing into ice on one hemisphere. Life thrives on gradients. It feeds on differences in temperature, chemical potential, energy availability. A world with stark contrast between its day and night sides would offer abundant gradients to exploit. Organisms could cluster along the terminator, that narrow band where the sun hangs perpetually on the horizon, where light and dark meet, where conditions remain stable but resources flow from both directions, or life could adapt to the extremes. Organisms on the day side might burrow underground, escaping the constant radiation, emerging only at night when transiting planets dim the star. Creatures on the night side might gather around hydrothermal vents, where heat from the planet's interior provides energy independent of sunlight. The atmosphere itself could host life, microorganisms drifting in the temperate zones between hot and cold, feeding on chemicals carried by winds. But TRAPPIST-1 is not alone. It has neighbours, close neighbours, planets that orbit near enough to see, near enough to influence, perhaps near enough to reach. During the system's violent youth, when asteroids and comets bombarded the inner worlds, material would have been ejected from surfaces with enough velocity to escape one planet's gravity and fall into another's. Rocks blasted from TRAPPIST-1 could have reached TRAPPIST-1d or TRAPPIST-1f within years, not millennia. And those rocks would have carried whatever microorganisms survived the journey. This process, called panspermia, is not theoretical fantasy. We have found meteorites on Earth that originated on Mars, ejected by ancient impacts, drifting through space for millions of years before falling to our surface. If life existed on Mars when these rocks were ejected, it might have survived the journey, frozen in the rock's interior, protected from radiation, waiting. In TRAPPIST-1, the distances are shorter, the transfer times faster, the probability of successful panspermia far higher. If life emerged on one world, it might have spread to all of them, not through intention or technology, but through the simple mechanics of impact and ejection. A single biosphere distributed across multiple planets, each one seeded by the others, each one hosting variations of the same fundamental biochemistry. Imagine the implications. Life on TRAPPIST-1e looks up and sees TRAPPIST-1d hanging in the sky. Not a dead world, not a sterile rock, but a cousin, a sibling, a place where chemistry followed the same path, where organisms share a common ancestor that lived billions of years ago on a world that no longer remembers its name. Evolution would proceed independently on each planet. The environments differ, the selection pressures vary. Over millions of years, life would diverge, adapting to local conditions, developing unique forms. but the genetic code might remain similar enough to reveal the connection, like languages descended from a common root still recognizable despite centuries of separation. Would such a civilization, if it arose, understand this connection? Would they recognize that the planets in their sky were not just neighbors but relatives? That life on their world and life on the next were branches of the same tree? Perhaps they would discover it through observation. Telescopes powerful enough to analyze the atmospheres of neighboring planets would detect biosignatures, oxygen, methane, dimethyl sulfide, the chemical signatures of biological activity. They would see that they were not alone, that life had not emerged once but persisted across multiple worlds, that their sky was not just crowded with planets, but teeming with biology. The psychological shift would be profound. Humans have spent centuries wondering whether life exists elsewhere, whether we are unique or common, whether the universe is hospitable or hostile to biology. A civilization in TRAPPIST-1 would never face that uncertainty. They would grow up knowing that life fills the cosmos, or at least fills their corner of it. The question would not be whether life is common, but how it spreads, how it adapts, how it endures across different environments, and they would have a laboratory to study it. Not distant exoplanets requiring generations to reach, but nearby worlds, close enough to observe in detail, perhaps close enough to visit. The energy required to travel between TRAPPIST-1 planets is vastly lower than interplanetary travel in our solar system. The distances are shorter, the gravitational wells shallower, the transfer windows more frequent. A civilization at our current technological level, capable of reaching Mars with months-long journeys, could reach neighboring TRAPPIST-1 planets in weeks. This proximity changes the calculus of exploration. In our system, space travel is expensive, difficult, reserved for nations and corporations with immense resources. In TRAPPIST-1, it might be commonplace, accessible, something individuals or small groups could attempt. The barrier between worlds would be lower, more permeable. Would such a civilization colonize its neighbors or simply visit them? Will they preserve the native biospheres, studying them as natural experiments in evolution, or would they reshape them, introducing their own organisms, engineering the planets to suit their needs? Perhaps they would do both. Perhaps some planets would remain pristine, protected as biological reserves, while others were transformed, their atmospheres adjusted, their surfaces cultivated, their ecosystems merged with imported life. Or perhaps life would not need help spreading. Perhaps it would be spreading already continuously through the ongoing exchange of material between planets. Every large impact launches debris into space. Some of that debris falls back, some escapes, some reaches neighboring worlds. If those worlds are habitable, if the microorganisms survive the journey, they seed new environments, establishing footholds, beginning the slow process of adaptation. In this sense, the TRAPPIST-1 system might not host 7 separate biospheres. It might host one distributed biosphere, fragmented across multiple planets, connected by the occasional exchange of life-bearing rocks, evolving in parallel but never entirely isolated. Earth's biosphere is confined to a single planet. We are alone on our world, separated from any potential neighbors by distances that biology cannot cross without technology. But in compact systems, biology might span multiple worlds naturally, without consciousness, without intent, simply through the mechanics of gravity and impact. This possibility suggests a different model for how life spreads through the universe. Not through deliberate interstellar travel, not through rare transfers across light years of emptiness, but through local exchange within planetary systems, life hopping from world to world within the same gravitational neighbourhood, establishing networks of related biospheres that share ancestry but develop independently. If this model is correct, then life in the universe might not be distributed as isolated instances, single biospheres scattered across vast distances. It might cluster, concentrating in compact systems where planets orbit close enough for panspermia to operate efficiently. Life would be common in such systems and rare elsewhere, creating a patchy distribution determined not just by the presence of habitable worlds, but by their proximity to each other. TRAPPIST-1 might not be unique in hosting life. TRAPPIST-1F might host it too, and TRAPPIST-1G, and perhaps even the inner worlds, TRAPPIST-1B and C, too hot for surface life but possibly harbouring organisms in subsurface oceans, protected from radiation by kilometres of rock and ice. Each world would tell a different story. Life adapting to high temperatures, life surviving in darkness, life thriving under thick hydrogen atmospheres, life finding ways to persist in environments we would consider extreme, demonstrating the flexibility of biology, the creativity of evolution when given time and resources. From Earth, we search for biosignatures in exoplanet atmospheres, hoping to detect the chemical imbalances that indicate life. In TRAPPIST-1, those searches might find not one biosignature but several, each planet contributing its own signal, each one revealing a different expression of the same underlying chemistry. And the inhabitants, if they exist, would not search for life in distant systems. They would observe it directly, watching their neighbours, studying the worlds overhead, learning from the natural experiments playing out in real time across their planetary neighbourhood. Perhaps civilizations are born not in isolation, but in neighbourhoods. Perhaps intelligence emerges more readily when life can see itself reflected in multiple worlds, when the existence of biology becomes not a question, but an obvious fact, visible overhead every night. Perhaps we are the anomaly, alone on a single world, our planetary siblings either too hot or too cold, our nearest neighbours lifeless or long dead. Perhaps compact systems like TRAPPIST-1 are where life becomes not just possible but inevitable, where chemistry crosses the threshold into biology not once but repeatedly, where evolution proceeds with multiple datasets, multiple experiments, multiple chances to succeed. If you stood on TRAPPIST-1E and looked up at TRAPPIST-1D, you would not be looking at an alien world. You would be looking at home, a variation on the theme, a different expression of the same fundamental pattern. Life recognizing itself across the darkness, separated by distance but connected by history, alone on each world but together in the system. The universe, in places, might be far more alive than we imagine. Not everywhere, not uniformly, but in certain configurations where planets cluster close and conditions align, life might not just survive, it might flourish, spreading across multiple worlds, creating not isolated biospheres but interconnected webs of biology, systems where life becomes the rule rather than the exception, and we would be searching for it from outside, looking in, wondering what we might find if we could stand on one of those surfaces and look up at a sky filled not with emptiness but with living worlds. Harmony is not permanent. For all the elegance of TRAPPIST-1, for all the mathematical beauty of its resonance chains, the system exists on a knife's edge. The same gravitational precision that maintains its stability also makes it vulnerable. Change one element, shift one orbit by a fraction of a percent, and the entire architecture could unravel. This is not speculation. Computer simulations demonstrate it repeatedly. Take the TRAPPIST-1 configuration, and alter the mass of a single planet by 5%. Run the simulation forward a few million years, watch what happens. At first, nothing changes. The orbits remain stable, the resonances hold. But small perturbations accumulate. The altered planet's gravity pulls slightly differently on its neighbours. Their orbits shift microscopically in response. Those shifts change how they interact with the next planet in the chain. The effects cascade outward, slowly at first, then faster. Within 10 million years, the resonances begin to break. One planet drifts out of its 3.2 ratio, falling into a 7.5 ratio instead, then into something irregular, no longer locked to its neighbours. Its orbit becomes chaotic, unpredictable. It swings closer to the inner planets, gravitationally disturbing them. They scatter. In some simulations, planets collide, merging into larger worlds surrounded by debris rings. In others, they are ejected entirely, flung out of the system into interstellar space, orphaned worlds tumbling through the darkness between stars. In still others, they spiral inward, falling into the star, consumed by the very sun that once warmed them. The final configuration bears no resemblance to the original. Where there were 7 worlds in harmony, there might be 3 in chaos, their orbits eccentric and unstable, their futures uncertain. The planetary symphony has become noise. This fragility is not unique to TRAPPIST-1. It is inherent to all compact systems. Kepler-36 contains 2 planets that orbit so close to each other they nearly touch. Every 97 days they approach within 1.2 million miles, less than 5 times the Earth-Moon distance. At that range, each planet appears 30 times larger than our Moon in the other's sky. The tidal forces are immense, flexing the planet's interiors, generating heat through friction, possibly driving volcanic activity on both worlds. The configuration is stable now, maintained by a delicate balance between their orbital periods and gravitational interactions. But stable does not mean permanent. Any external perturbation, a passing comet, a distant stellar flyby, could push one planet slightly off course. The tight spacing leaves no room for error. A small deviation becomes a large one within a few orbits. The planets that once danced together would begin a collision course. TOI 178 showcases a different kind of fragility. 6 planets locked in resonance, their orbits synchronized in a chain that astronomers initially thought was impossible. The planets' densities vary wildly, one as fluffy as cotton candy, another as dense as iron, arranged in no obvious pattern. Theory suggests planets should sort themselves by composition, heavy ones close to the star, light ones farther out. TOI 178 ignores that rule. This suggests a violent past. Perhaps the planets formed in a different configuration and were scattered by gravitational interactions, only later settling into their current resonance. Perhaps they suffered massive impacts that stripped away portions of their atmospheres or added material from elsewhere. Perhaps the system is still recovering from chaos, its current harmony temporary, a brief pause before the next reshuffling. The timescales involved are difficult to comprehend. A system can remain stable for millions of years, even hundreds of millions, before instability suddenly emerges. To an observer, the system would appear eternal, unchanging, its orbits as reliable as clockwork. But beneath that apparent stability, small effects accumulate, perturbations add up, chaos waits. Even the most stable systems are not immune. Our own solar system, with its wide spacing and well-separated planets, is not guaranteed to remain in its current configuration. Long-term simulations extending billions of years into the future show small probabilities of catastrophic instability. Mercury's orbit could destabilize, sending it crashing into Venus or the Sun. Jupiter and Saturn's gravitational interactions could slowly push Neptune outward, potentially ejecting it from the system entirely. These events are unlikely within the Sun's remaining lifetime, but they are not impossible. Given enough time, chaos finds a way. Resonances that held for billions of years can break. Orbits that seemed eternal can drift. The solar system we inhabit is not its final form. It is simply the current snapshot in an ongoing evolution that will continue long after Earth becomes uninhabitable. Compact systems face these dangers on accelerated timescales. The planets interact more frequently, their gravitational influence is stronger, their orbits more tightly coupled. What takes billions of years in our system might take only millions in theirs. Stability, in this context, is relative. There is also the star to consider. Red dwarfs like TRAPPIST-1 are prone to flares, sudden releases of energy that can temporarily brighten the star by factors of 10 or more. During the star's youth, these flares were frequent and violent, stripping atmospheres from the inner planets, bombarding them with radiation. Even now, billions of years later, flares still occur. Less frequently, but still powerful enough to affect planetary environments. A major flare could inject energy into the atmospheres of tidally locked planets, driving massive storms, disrupting weather patterns, potentially altering the delicate balance that keeps water liquid on their surfaces. If flares became frequent enough or powerful enough, they could erode atmospheres entirely over geologic time, leaving once habitable worlds stripped and barren. And there are external threats. The galaxy is not empty. Stars move through space, sometimes passing close to each other. A star passing within a few light years of TRAPPIST-1 could gravitationally perturb the outer planets, changing their orbits enough to break the resonance chain. The system would have no defense, no way to restore the balance once lost. Rogue planets, ejected from their own systems, wander the galaxy in vast numbers. Some estimates suggest there may be more rogue planets than stars. If one passed through TRAPPIST-1, even without directly colliding with anything, its gravity could scatter the planets, ending billions of years of stability in a single chaotic encounter. Even within the system, stability requires specific conditions to persist. The planets must maintain their current masses. If tidal forces or atmospheric escape gradually change a planet's mass, the resonances could drift out of alignment. The orbits would need to adjust, but there is no guarantee they would find a new stable configuration. Collapse becomes possible. In some ways, these systems resemble ecosystems. Remove one species and the entire web can unravel. Change one variable and cascading effects ripple through the structure. Complexity creates both beauty and vulnerability. The more tightly integrated the system, the more susceptible it becomes to disruption. Perhaps this is why such systems are rare, not because they cannot form, but because they cannot last. For every TRAPPIST-1 we observe, there might be dozens of similar systems that formed and then destroyed themselves, their planets colliding or escaping, their resonances breaking under the weight of accumulated perturbations. We see the survivors, the systems that happen to form with just the right masses, just the right spacing, just the right isolation from external threats. The others left no trace beyond scattered debris. Even the most beautiful song can fall out of tune. A missing note, a wrong tempo, and harmony becomes discord. The universe does not preserve its creations forever. It builds them, admires them for a while, and then allows them to decay, making room for new configurations, new experiments in gravitational architecture. For the inhabitants of such worlds, if they exist, this fragility would shape their entire worldview. They would live knowing that their home is not eternal, that the balance maintaining their existence is delicate, that forces beyond their control could end everything. Perhaps they would develop philosophies of impermanence, recognizing that all structures, even planetary systems, are temporary, or perhaps they would not think about it at all. Just as we rarely contemplate the slow drift of continents or the eventual death of the sun, they might accept their system's stability as a given, never questioning whether the planets will still be there tomorrow, never calculating how long the resonances can hold. But the universe calculates. It tracks every perturbation, every gravitational tug, every energy exchange. And eventually, when the numbers no longer balance, when the equations demand change, the system will respond, not out of malice or intent, but simply because that is what physics requires. The fragile balance will shift, the harmony will break. And somewhere, in the darkness between stars, a planetary system that endured for billions of years will begin its final transformation, from order into chaos, from music into silence. Until then, the planets continue their dance. 7 worlds turning together, their rhythms synchronized, their futures uncertain. They move through space as they have for eons, unaware that they exist on borrowed time, that the very precision that keeps them stable also makes them vulnerable. That harmony and fragility are not opposites but partners, inseparable aspects of the same cosmic truth. Stability is not distance, it is rhythm. But rhythm, no matter how perfect, is not forever. Look closer at any structure in the universe and you find another structure waiting inside. A galaxy contains billions of stars. Each star contains planets. Each planet contains moons. Some moons contain subsurface oceans. Those oceans contain chemistry. Chemistry contains molecules. Molecules contain atoms. Atoms contain particles. And within those particles, fields and vibrations, patterns nested within patterns. Complexity folding into itself across scales that span from the width of the observable universe down to dimensions smaller than we can measure. This is not merely description. It is architecture. The universe builds in layers, each one echoing the others, each one following similar rules despite operating at vastly different scales. Consider a planetary system. Planets orbit a star, held in place by gravity, moving in ellipses determined by their velocity and the star's mass. Now consider a moon orbiting one of those planets. It follows the same laws, the same mathematics, the same elliptical paths. The scale changes, the masses differ, but the pattern remains identical. Zoom out. Our solar system orbits the centre of the Milky Way, taking 230 million years to complete one circuit. We are not stationary. We orbit just as Earth orbits the Sun, held by the same gravitational principles, following the same types of trajectories. The Milky Way itself moves through space as part of the local group, a collection of galaxies bound together gravitationally, orbiting their common centre of mass. Zoom in. Electrons orbit atomic nuclei, not because of gravity but because of electromagnetic force. Yet the mathematics are strikingly similar. Central mass, orbiting objects, stable configurations, resonances. Even at the quantum scale, where classical mechanics breaks down and probability replaces certainty, the patterns echo what we see in planetary systems. This self-similarity extends beyond orbital mechanics. Look at the structure of matter distribution in the universe. Galaxies cluster into groups. Groups cluster into superclusters. Superclusters form filaments and walls. vast structures stretching across hundreds of millions of light years, surrounding enormous voids. The pattern resembles foam or neural networks, or the structure of lungs branching airways into increasingly fine passages. Now look at a planetary system with moons. The major moons orbit the planet, but those moons have their own gravitational influence, creating gaps in debris rings, shepherding smaller moonlets into stable orbits. Those moonlets might have their own dust clouds, tiny particles orbiting in turn. At every level, the same hierarchical structure repeats. Large objects surrounded by smaller objects, held together by gravity, arranged in patterns that maximize stability. Saturn's rings demonstrate this beautifully. From a distance, they appear as smooth bands. Look closer and you see gaps, divisions carved by the gravitational resonances of Saturn's moons. Look closer still, and each ring subdivides into thousands of narrower ringlets. Closer again, and you find that each ringlet contains individual particles, ice chunks ranging from dust grains to house-sized boulders, each one orbiting independently but collectively, creating the appearance of solid structure. The rings are not solid, they are not even continuous. They are trillions of separate objects, each following its own orbit, but together forming patterns visible from hundreds of millions of miles away. This is emergence, complexity arising from simple rules applied across vast numbers of individual components. Compact planetary systems like TRAPPIST-1 are themselves nested structures. 7 planets orbit a star, but those planets likely have moons, though we cannot yet detect them at that distance. Those moons might have debris rings. The rings contain particles. Each level follows the same gravitational choreography, scaled to its local environment, and if those planets host life, the nesting continues downward. Organisms contain organs. Organs contain cells. Cells contain organelles. Organelles contain molecules organized into metabolic pathways. Each level exhibits structure, organization patterns that repeat across scales. A cell's membrane separating interior from exterior mirrors a planet's atmosphere separating surface from space. Both are boundaries, both are semi-permeable, both maintain gradients that enable complexity. This fractal quality suggests something profound about physical law. The universe does not require different rules for different scales. It uses the same principles everywhere: gravity here, electromagnetism there, quantum mechanics deeper down, but the behavior patterns they produce echo across levels. A spiral galaxy and a hurricane follow different forces but create similar shapes. A branching river delta and a branching network of blood vessels solve the same optimization problem: how to distribute flow efficiently across space. Perhaps this is why the universe is comprehensible to us at all. We are mid-scale creatures existing between atoms and galaxies. We can look downward and see patterns we recognize from our own experience. We can look upward and see those same patterns playing out on cosmic stages. The mathematics that describes planetary orbits also describes electron clouds. The statistics that govern gas behavior also govern star clusters. There is a philosophical weight to this recognition. It suggests that the universe is not a collection of unrelated phenomena, but a unified structure, variations on common themes, a single pattern expressed through different media. Whether you're examining a planetary system or a biological cell or a galactic supercluster, you're looking at manifestations of the same underlying order. This realization changes how we think about our place in the cosmos. We're not separate from these patterns, we are made of them. The calcium in our bones was forged in stellar cores. The water in our cells cycled through comets. The atoms in our bodies have orbited the galactic center 20 times since the Sun formed. We are not observers of the nested universe. We are part of it, temporary arrangements of matter participating in the same patterns that organize galaxies. Some scientists speculate that this nesting extends beyond what we can observe. Perhaps our universe is itself nested within a larger structure, a multiverse where entire universes orbit some higher dimensional center, following gravitational rules we cannot yet perceive. Perhaps the Big Bang was not a beginning but a transition, our cosmos budding off from a parent structure, carrying with it the mathematical patterns that now govern physics. Others suggest the nesting goes deeper inward. Perhaps particles are not fundamental but contain inner structure, layers we have not yet detected because our instruments cannot probe those scales. Perhaps quarks are made of preons, which are made of something else, an infinite regression of nested complexity extending downward forever. We cannot know whether the nesting is infinite in both directions, but we can observe that every time we gain the ability to look closer or farther, we find new levels of organization, new patterns that echo the ones we already know. The universe seems inexhaustibly deep, each answer revealing new questions, each scale containing surprises but also familiar architectures. In TRAPPIST-1, the nesting is visible. Planets orbit the star in resonance chains. Those planets likely have moons orbiting them in miniature resonance chains. Those moons might have rings, particles in resonance with shepherd moons. If life exists there, organisms will contain nested structures, cells within organs, within bodies, within ecosystems, within biospheres. And if intelligence emerges, it might build nested structures of its own, cities within regions, within nations, within planetary civilizations. Each level would operate according to its own rules, but would also participate in the rules of the level above and below. A cell must function as a cell, but it must also serve the organ. An organ must function as an organ, but it must also serve the organism. A planet must orbit as a planet, but its orbit must harmonize with the system. This is not constraint. It is integration. Each level is both autonomous and connected, both independent and interdependent. The pattern holds from quantum fields to galaxy clusters, a cosmic architecture where nothing exists in isolation, where every structure is nested within larger structures and contains smaller structures, where the universe reveals itself as Russian dolls extending infinitely inward and outward. Perhaps our solar system is a micro-resonance within a larger pattern we've not yet perceived. Perhaps the Sun's orbit around the galactic center is locked in resonance with other stars, creating a rhythm too slow for human lifetimes to detect. Perhaps the Milky Way's dance with Andromeda is part of a resonance chain spanning the local group. The mathematics would be the same, the principles identical, only the scale changes. From atoms to solar systems, the pattern repeats. Not because the universe is simple, but because it is elegant. It has found solutions that work at every scale, principles that apply equally to electrons and planets and galaxies. It does not need infinite variety. It needs only a few fundamental rules, applied recursively, nested within themselves, creating complexity through repetition rather than complication. This is the lesson of the nested universe. Everything is connected not through mysticism but through structure. The same patterns that organize planetary systems organize cells. The same mathematics that describes orbits describes economies and ecosystems. We live within layers, each one following its own logic but echoing the others, creating a cosmos where nothing is truly separate, where every scale reflects every other scale, where patterns repeat endlessly across dimensions we can barely imagine. And somewhere within those nested layers, we exist. Not at the center, but not at the edge either. Somewhere in the middle, large enough to contain atoms, small enough to fit within galaxies, perfectly positioned to perceive the patterns above and below, to recognize that we are not observers of the nested universe but participants in it. One more layer, an architecture that extends beyond perception in both directions. The universe builds in layers, and every layer is a world inside a world. We have spent our entire history looking up at empty skies. Venus appears as a bright point, Mars as a red wanderer, Jupiter and Saturn as distant lights that move slowly against the background stars. We can see them, but we cannot know them. They remain abstractions, worlds we imagine but cannot touch, surfaces we theorize about but cannot observe in detail. This distance has shaped us. It has made us feel alone. We evolved on a world with no visible neighbours, no sibling planets hanging overhead, no constant reminder that other surfaces exist within reach. The sky we inherited is vast and mostly empty, filled with stars too distant to ever visit, galaxies too remote to ever influence us. We learn to see ourselves as isolated, a single island of complexity in an ocean of void. But isolation is not universal. It is not even common. The universe prefers to build neighborhoods. Systems like TRAPPIST-1, where planets cluster close enough to see each other's weather, appear throughout the galaxy. Kepler has found hundreds. TESS continues discovering more. These configurations are not rare accidents. They are standard products of planetary formation, perhaps more typical than our own widely scattered arrangement. This suggests something uncomfortable. We might be the outliers. Our isolation might be the exception, not the rule. Most planetary systems form in compact configurations. Planets migrate inward, lock into resonances, settle into tight orbits where proximity becomes the defining characteristic. If life emerges in such systems, it grows up knowing it is not alone. Other worlds are visible, present, undeniable. The question is not whether life exists elsewhere, but how to reach the neighbours overhead. For us, the search for life has meant looking outward into emptiness, hoping to find biosignatures in the atmospheres of planets, orbiting distant stars, civilizations that might have existed billions of years ago, signals that have travelled across such vast distances that the senders are likely extinct by the time we receive them. We search knowing we may never find answers, that even if we detect life, we will never meet it, never communicate with it in any meaningful time frame, never bridge the distances that separate us. But in compact systems, life would not need to search, it would look up and see. The psychological difference is profound. A civilization on TRAPPIST-1e would not wonder whether they are alone. They would know with direct observational certainty that other worlds exist within their system, that those worlds might harbour life, that the cosmos is not empty but crowded, not hostile but hospitable to biology. This would change their philosophy, their religions, their approach to exploration. Where we have built our worldview around cosmic loneliness, they would build theirs around cosmic community. Where we see the universe as indifferent, they might see it as deliberately structured for connection. Where we treat isolation as normal, they would treat it as tragic. Perhaps this explains the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilizations and our failure to detect them. We have been looking for signals from civilizations that spread across star systems, that built interstellar communication networks, that saw the galaxy as a frontier to conquer, but perhaps most civilizations never develop that perspective. Perhaps most emerge in compact systems where exploration means travelling to neighbouring planets, not neighbouring stars. Where communication happens across millions of kilometres, not light years. Where the challenge is not whether to reach other worlds but how to coexist with them. Such civilizations might never build radio telescopes pointed at distant stars. They would have no reason to. Their neighbours would be visible overhead, reachable within lifetimes using conventional rockets. Why search the depths of space when the answer to "Are we alone?" is written across your own sky every night? This perspective reframes our understanding of cosmic significance. We have always measured importance by rarity. If life is rare, we tell ourselves, then we are special, meaningful, worth preserving. If life is common, some fear we become trivial, just another instance of a universal pattern, unremarkable in a cosmos filled with biology. But compact systems suggest a different measure of significance: connection. What matters is not whether you are alone, but whether you are isolated. A civilization in TRAPPIST-1, even if life is common throughout the universe, exists within a web of relationships. Planetary siblings that share history, perhaps share biology, certainly share a gravitational architecture that binds them together. We, despite possibly being rare, exist in isolation. No neighbours close enough to observe, no sibling planets to inspire us, no visible reminder that surfaces other than Earth exist within human reach. Our rarity, if we are rare, does not make us significant. It makes us lonely. Perhaps the lesson of these worlds is simple. Life thrives not in isolation, but in harmony. This applies at every scale. Planets survive not by avoiding each other, but by synchronizing with each other. Biology spreads not through isolation, but through exchange. Panspermia carrying microbes between neighbours, creating distributed biospheres that share ancestry. Intelligence might emerge not from solitary contemplation, but from the necessity of navigating relationships with visible neighbours, learning to coexist in systems where collision is always possible. Even within ourselves, the pattern holds. We're not individuals, we're ecosystems, trillions of bacteria living in our bodies, mitochondria descended from ancient symbiosis, viruses integrated into our DNA. We exist because of connection, because different forms of life learn to cooperate rather than compete, to harmonize rather than destroy each other. The universe, it seems, has always preferred cooperation over isolation. From quantum entanglement to orbital resonance to biological symbiosis, the fundamental structures of reality favor systems that interact, that influence each other, that become more stable through connection rather than separation. Our isolation has made us forget this. We built civilizations around competition, nations around borders, philosophies around individualism. We see ourselves as separate from nature, separate from each other, separate from the cosmos. We look at the night sky and see emptiness, see distance, see proof that we are alone and must fend for ourselves. But compact planetary systems tell a different story. They show us what the universe actually builds when left to its own physics. Neighbourhoods, not hermitages. Harmony, not chaos. Structures where proximity enables complexity rather than destroying it. If we could stand on TRAPPIST-1D and look up, we would see what we've been missing. Not emptiness, but presence. Not isolation, but connection. Not a universe indifferent to life, but a universe structured in ways that make life not just possible, but inevitable. Not just rare, but distributed. Not just lonely, but interconnected. The 7 planets of TRAPPIST-1 do not orbit in isolation. They orbit together, their paths intertwined, their futures dependent on each other's stability. If one were removed, the others would drift. If one changed, the others would respond. They are not separate worlds that happen to orbit the same star. They are a single system, a unified structure, a community held together by the invisible threads of gravity. This is what we have been searching for. Not life elsewhere, but proof that connection is fundamental, that the universe does not build walls, that proximity, far from being dangerous, is the foundation of everything stable and beautiful. We are learning this slowly. We discover compact systems and marvel at their complexity. We find exoplanets in resonance chains and wonder how they remain stable. We detect biosignatures in multiple worlds within the same system and begin to understand that life might prefer neighborhoods to solitude. But we have not yet internalized the lesson. We still think of exploration as leaving home, of discovery as finding things far away, of significance as being unique. We have not yet embraced the possibility that our importance might lie not in our rarity, but in our eventual connection to something larger, that our destiny might be to join a cosmic community rather than stand apart from it. The compact systems scattered throughout the galaxy are not just scientific curiosities, they are invitations. They show us what is possible when worlds choose proximity over distance, when gravity writes music instead of chaos, when isolation gives way to harmony. Somewhere beneath a dim red sun, 7 worlds still turn together, their skies forever shared, their orbits forever synchronized, their existence proof that the universe's oldest law is not survival of the fittest, or entropy, or the speed of light. It is harmony, and if we listen carefully enough, across the silence and the distance, we might hear the faint echo of their rhythm, reminding us that we were never meant to be alone, that isolation is not our nature, that somewhere in the architecture of reality itself is a pattern we have forgotten but might yet remember. The pattern that says, worlds belong together, life flourishes in proximity, and the deepest truth of existence is not separation, but connection, not distance but nearness, not silence but the quiet symphony of planets moving in time, drawing close, holding together, turning as one beneath a sky that refuses to be empty.